So it's called the effectiveness NTU method. Okay. NTU stands for number of transfer units. While we derive this Epsilon-NTU method, you will see the definition of NTU, so I will not go over it now. Now, what's important here is that the genesis of this method is based on the fact that in industries, often these heat exchangers are connected to a reactor or connected to an outlet stream, connected to a stirrer or something, some other process equipment. Therefore, often we do not know outlet temperature a priori. This is very important. You may not know it a priori. Okay. So remember that once you have fabricated a shell and tube heat exchanger, there is no point in working out the design after that. So you are interested to work out the design before you fabricate the heat exchanger. That's one possibility. The second possibility is, suppose I want to modify my process. Okay. So remember I told you this battery example where they make gamma MnO2. So it's the same plant which manufactures the acidic and the alkaline gamma MnO2. So in order to manufacture different chemicals, you do not construct a new plant. You always attempt to maximize the equipments and the process that you have built. Therefore, it's often you may realize that you may not know what is the exact outlet temperature, or sometimes it could be vice versa. Your outlet temperatures may have been specified because you may know what should be the initial conditions for the or the inlet conditions for a reactor, but you may not know what is the inlet conditions for the heat exchanger because it comes from some other process. So it turns out that under many industrial settings, only two of the four temperatures may be known. I may even say that may be specified, because remember that you are always interested in designing before fabrication. So only two of the four temperatures may be specified. Now if you use delta T LMTD method, remember that when we use this delta T LMTD example, we saw that suppose if we know three temperatures, we can find the fourth one. So if we know any three, we should be able to find the fourth one by simply writing an m dot Cp delta T equal to the m dot Cp delta T for the cold stream. Okay. But then if only two temperatures are specified, you can still use delta T LMTD. It doesn't mean that you cannot use it. The way to do that is, so you have Q is m dot Cp hot fluid, delta T hot fluid, okay. You actually got three equivalences using this relationship. So you could guess what is one of the temperatures. So you could guess so the first step would be, let's say that the THI and TCI are given to you. The inlet temperatures of the hot and the cold fluid are given to you. Okay. Now we don't know what are the THO and TCO are not known. Okay. We don't know these two. We only know these two quantities and we don't know these two quantities. So if I use the delta T LMTD method, the way to go about is, okay, I can guess what should be the THO. I can guess that. Okay. From this I can estimate TCO. I can do that because I can always write a simple MCP delta T equivalence and I can find out the cold outlet temperature. Then from here I can find out UA delta T LMTD, assuming that the area and the heat transport coefficient is known. I can find out delta T LMTD. Now obviously this is not going to match with the m dot Cp delta T, right? This is not going to be equal to and that's not going to be equal to m dot Cp cold, simply because the initial guess that you made is not right. I mean, we know that it's not right, it's a guess. So one could actually set up an iterative problem. Okay. So one could set up an iterative problem How do you set up an iterative scheme? We know what is Q based on this, and we know what is UA delta T LMTD. So we should be able to independently estimate what is TCO based on this guess. So we could use TCO as an objective temperature, and then we can minimize the error that you would get by estimating TCO from these two expressions. That's one way. There are many ways to do this, many ways to pose this problem. So one needs to use an iterative scheme in order to estimate all four temperatures. So that's not a very easy thing to do. So in fact, in this premise is what the Epsilon-NTU method was actually discovered, where you don't have to follow such cumbersome iterative scheme. You can simply use the Epsilon-NTU method, which gives you a very elegant way to design the heat exchanger under this kind of a situation. And that's what we are going to see for the rest of the class today. So I define epsilon as the efficiency or the effectiveness of the heat exchanger. Okay. So epsilon is the effectiveness of the heat exchanger, and that is simply defined as the actual amount of heat that is transported, which is Q, divided by the maximum possible heat transport. So now if I know how to estimate Q max, I am done. I can find out what is the efficiency of heat transport. How do I find Q max? What is the maximum possible temperature difference in any heat exchanger? Maximum possible. Delta T? Not really. We know that. So for example, if I take a counter flow, okay, it's definitely not the case in a parallel flow. We know that. Okay. Suppose I take a counter flow, okay. So this is the temperature profile that you would get. It's not parallel. Let's say this is the temperature profile. Okay. So this is the hot stream and this is the cold stream. Okay. So TCI and TCO. Okay. Now I can always have a situation. Okay. The temperature of the cold stream is always going to increase, right? It's never going to decrease. It's always going to increase because it's always gaining sensible heat. Now, what is the maximum possible temperature difference when I maintain the cold stream at a constant temperature? That's the maximum possible temperature difference in a counterflow, where the temperature of the cold fluid does not change. How can I achieve this? We looked at some of the special cases. I can do the same thing. Right. So if yes, exactly. So you can do it either way. It doesn't matter. So all it simply means that this is the maximum possible temperature difference that you can achieve in the heat exchanger at any location. You can look at any location you want, and this is the maximum possible. This is the theoretical maximum possible temperature difference that you can achieve. Okay. So now, having said that, can we find out what is the So if we know the maximum possible temperature difference, how do we find the maximum possible heat transport rate. Remember, we want Q max. We don't want delta T. Actually, we want delta T max, but really to define efficiency, what we need is Q max. We need the maximum possible heat transport rate. So how do we find that? Remember that Q is simply defined as sum m dot Cp into delta T. Okay. So one could intuitively guess that Q max has to be something to do with delta T max, but the question is what m dot Cp that you should use. See, we have two m dot Cp's here. We have m dot Cp of hot fluid or m dot Cp of cold fluid. Which one should we use to define the maximum heat transport rate? One that is higher. Why? No, not really. Suppose I say that, say under steady state conditions, okay, m dot Cp of cold fluid THO, right? So that's the simple steady state balance. Now suppose if I say that m dot Cp of the cold fluid, okay, if it is lesser than m dot Cp of the hot fluid, okay. Now the exercise is to find out theoretically which of these two streams is actually going to reach the maximal temperature difference, right? So really what you need to use to find the maximum heat transport rate is find out theoretically as to which stream is likely to achieve the theoretical temperature difference. Only that stream's m dot Cp is what you have to use to find out the maximal heat transport rate. Okay. So Q max is m dot Cp of that stream, I call it m, let's say, okay, delta T max. So the exercise is to find out which stream is going to theoretically achieve the maximal temperature difference. How do we find this? So if m dot Cp of C is less than m dot Cp of H, okay, which one will have the maximal temperature difference? It's the cold fluid. So it's very easy to see that. So TCO minus TCI will always be greater than THI minus THO. So that gives you a very clear way to find out which stream is theoretically possible to have maximal temperature difference. So if the m dot Cp of the cold fluid is less than the m dot Cp of the hot fluid, then it is the cold fluid which will always achieve the maximal temperature difference. By cold fluid for this example. So if we specify, suppose that this is the m dot Cp of the cold fluid is lesser than the m dot Cp of the hot fluid. So remember that these are the Cp is the property of the fluid and m dot is the flow rate. So these are actually m dot is a controllable parameter because you have a pump which is going to flow the fluid, and Cp is an intrinsic parameter. So you should be able to control which one is maximum, which one is minimum. Okay. So the capacity of the fluid multiplied by the mass flow rate, whichever is minimum, that fluid stream is the one which will likely to have a maximal temperature difference. So therefore, Q max is essentially defined as m dot Cp minimum multiplied by delta T max. Okay. So this is an important observation. The maximum possible heat transport rate is essentially the product of the minimum m dot Cp between the two multiplied by the maximal temperature difference, which is the difference in the inlet temperatures of the two streams. Okay. So now we know how to define Q max. Okay. So we can simply define efficiency as, so if I define efficiency in terms of the cold fluid for this example, so it will be m dot Cp of cold fluid multiplied by TCO minus Tci divided by m dot Cp of cold fluid Thi minus Tci. Okay. So, this is by assuming m dot Cp of cold fluid is less than m dot Cp of hot fluid. Alright. So, therefore, suppose if, so this is a very generic definition. So, irrespective of which fluid is going to have maximal temperature, you can always define in terms of the minimum capacity multiplied by the maximal temperature difference. That should tell you what is the theoretical maximum possible heat transport rate. Okay. So, therefore, if suppose m dot Cp of the hot fluid is less than m dot Cp of the cold fluid, one can immediately define epsilon as Q by Q max m dot Cp hot fluid Thi minus Tho divided by m dot Cp of hot fluid Thi minus Tci. So, from here we can see that Thi minus Tho, that is equal to epsilon into Thi minus Tci. So, this provides a mechanism to eliminate the one of the temperatures. So, remember that we have got inlet temperatures in this expression here. It provides a mechanism to eliminate the one of the temperatures, that is, we could eliminate Tho from here. So, we will see how to do that in a short while. Okay. So, what it simply means is that we need to know only the efficiency of the heat exchanger. If we know the efficiency of heat exchanger, then we are able to independently estimate the outlet temperature of the hot fluid based on the inlet temperature. So, let us take the case of a parallel flow. Okay. So, you may recall from the last lecture. So, delta T that is equal to, does anyone remember, minus UA into 1 by m dot Cp cold plus 1 by m dot Cp hot. Okay. Because if you modify this, what you will get is Q equal to UA delta T LMTD is what you will get. Okay. So, now suppose I assume that m dot Cp of the hot fluid is the minimum. Okay, assume that it's smaller than the m dot Cp of a cold fluid. Okay. So, now I can rewrite this as minus UA divided by m dot Cp min 1 plus okay. So, all I have done is I have just pulled out the minimum, that is, in this case it is the m dot Cp of the hot fluid. Okay. So, if I define Cr as the ratio of the capacities m dot Cp min to max, okay. So, I define m dot Cp min divided by m dot Cp max. Okay. So, I define that as Cr. So, I can plug this in here. So, what I will get is, so delta T minus UA divided by into 1 plus Cr. Now, this is Thi minus Tci, oops, exponential. Please add an exponential. Okay. So, T out is Tho minus Tco. So, that is why it is a parallel flow. We are looking at parallel flow divided by Thi minus Tci. That is the inlet stream. Okay. So, now we can rewrite this as Tho minus Thi. All I am doing is I am adding and subtracting the inlet and the outlet stream temperatures. plus Thi minus Tci divided by, okay, I haven't done anything spectacular here. All I have done is I have just added Ci and subtracted Ci, okay, and that should be equal to the exponential of whatever term that's present above. That goes. So we know that Thi minus Tho, that's equal to epsilon into Thi minus Tci, simply based on the definition of effectiveness. Okay. So from here we can substitute this. So what you will get is minus epsilon into Thi minus Tci, okay, plus Tci minus Tco divided by Cr. Okay. So now, so we have eliminated Tho from this expression. We need to eliminate Tco. How do we do this? How do we eliminate Tco? Using the heat balance. So we have m dot Cp of hot fluid divided by m dot Cp of cold fluid, okay, which is basically Cr. Remember that, that's the definition, right? That should be equal to Tco minus Tci divided by Thi minus Tho, right? So from here, can we find out what is Tci minus Tco? Can we eliminate Tco from here? Is it possible? Of course, yes. We know that Thi minus Tho is epsilon Thi minus Tci. So that's nothing but Tco minus Tci divided by epsilon into Thi minus Tci. Okay. So we can simply plug this in here. So that will be minus epsilon Thi minus Tci plus Thi minus Tci minus. So all I have to do is now to completely I can eliminate Tci and Tco from here. So that will be epsilon Cr Thi minus Tci. Okay, that divided by Thi minus Tci, that should be equal to exponential minus Ua by m dot Cp min into 1 plus Cr. So now I can cancel out Thi Tci from here, and so what I get is, so there will be minus epsilon into 1 plus Cr plus 1, that should be equal to exponential of minus Ua by m dot Cp min into 1 plus Cr. Okay. So this Ua by m dot Cp min is what is called as NTU, called the number of transfer units. So look at this expression. So Ua, what is 1 by Ua? What's 1 by Ua? It's the resistance offered for heat transport between the two fluids, right? And what is 1 by m dot Cp min? It's the resistance offered by the fluid which has the maximum capacity to take heat, take sensible heat, right? Maximum. Remember, m dot Cp min is what is used for defining Qmax. Remember that Qmax is defined as m dot Cp min multiplied by delta Tmax. So this is the resistance that is offered by the fluid which has the theoretical capability to take maximum sensible heat. Okay. So the number of transfer units is actually an important design parameter. The resistance for heat transport between the two fluids depends upon the area of heat transport. So the design parameter comes in an NTU, and m dot Cp min tells you what's the resistance offered by the fluid which is capable of taking maximum possible heat. Okay. So therefore we can define, so the final expression would look something like this. So epsilon equal to 1 minus exponential of minus NTU into 1 plus Cr divided by 1 plus Cr. Okay. So all I have done is I have just manipulated this algebraic manipulation. Take this on the left hand side, take this on the right hand side, and find out what is epsilon. Okay. So if I know NTU, I can find epsilon. If I know epsilon, I can find NTU. So that's a very powerful method. Remember that, note that there is no temperature difference in this expression at all. Now if I know epsilon, I can find out what is the one of the temperatures. So remember that epsilon is given by Thi minus Tho divided by Thi minus Tci. So if I know NTU, which is simply dependent on UA and m dot Cp min, I can find epsilon, and if I know epsilon, I can find Tho. So the sequence would be, so the sequence of calculations would be, if I first is I find U, and second is I find NTU, which gives me, suppose I know the area of heat transport already, so I can find UA by m dot Cp min. Okay. Then from here I can estimate epsilon. So using the Epsilon-NTU relationship, from epsilon I can find out the outlet temperature of fluid stream with minimum m dot Cp. Okay, I can find out the outlet temperature of the fluid stream with minimum m dot Cp, or, and then how do I find the other temperature? Simply use heat balance, right? So we know that we can find Tco by using m dot Cp delta T hot fluid equal to m dot Cp cold fluid delta T cold. Okay. So what we have suddenly found is, we have found a powerful method. So even if you don't know the 2 of the 4 temperatures, you don't have to resort to the cumbersome delta T LMTD method. You can simply use the Epsilon-NTU method, which provides a nice and simple way to find out the temperatures. You can do vice versa. If you know one of these temperatures, you can actually use, you can do the reverse. If you know one of the temperatures, you can find the other one, you can find epsilon, you can find the NTU, and you can find the area. So you can do the reverse. If you want to find the area of heat transport for a given problem, you can do the reverse step and you will find the area of heat transport. If the area and the parameters of the heat exchanger is given, you can go forward and find out all the temperatures. So this is very useful, particularly if you want to use the same set of equipments for a slightly different process, and this is very, very common in industry. So it's never the case that you have individual units for manufacturing individual chemicals. They are always shared, particularly in pharma industries and many other places. It's all very shared. So if you know that you want to introduce a new process, if you want to introduce manufacture of new chemical, then you cannot dismantle the process. So with the existing process, you should be able to design your parameters such that you can use the existing equipments in order to achieve the desired output. So these kinds of reverse calculations are very, very useful for that kind of problem. So such a Epsilon-NTU has been worked out for all kinds of configurations. In fact, I would recommend that you should derive some of these and check it by yourself. I'm going to give you these expressions. So for a counter flow, epsilon is equal to 1 minus exponential of minus NTU into 1 minus CR divided by 1 minus CR exponential of minus NTU into 1 minus CR. So that's for the counter flow, okay. And for shell and tube heat exchangers, now this is for one shell pass and 2, 4, 6, etc. tube passes. Obviously, it has to be even number. Okay, so epsilon will be 2 1 plus CR plus 1 plus CR square to the power of 1 by 2 into 1 plus exponential of minus NTU square divided by 1 minus NTU to the power of minus 1. Let's bracket outside. Okay, so that's the expression for one shell pass, and this has been derived for all combinations of heat exchangers. Okay, so remember that. So we sort of finish all the theoretical aspects of heat exchangers. So what we are going to do next is we are going to look at some example problems and we'll march on to the next issue. Now before we do that, I want to emphasize this concept of NTU. It's the first time you are hearing in this course, and the first time probably you are hearing in a chemical engineering course. So this is something that you will see very often in many different calculations. You will see a lot more of the transfer unit concept, the transfer unit concept in your mass transport course, mass transport operation course. And in fact, you will see that when you design a tower, distillation tower or any column, the transfer units is used as a standard units for designing the height, designing what should be loading, etc. So NTU, this concept is an extremely important concept in chemical engineering, and I would strongly urge you to pay special attention to this and try to understand what this means. Remember that it's the ratio of the resistance offered for transport of heat from one fluid to the other divided by the resistance offered by the fluid which is capable of transporting or which is capable of taking up maximum possible heat transport. Okay, so that's an important definition, and similar definitions you will see under many different contexts.